Welcome to AP Calculus AB video for Skill 105. I can find the domain and range of a function graphically and algebraically. And the trivia question for the lesson is, below is a feature of the Parthenon, and this is the stylobate, and what is being demonstrated with this sketch? Alright, so what we have here is a diagram which shows what a function does. It takes an input and it does some sort of rule to it and gives you an output. Another name for input is domain or independent variable, and another word for output is range or dependent variable. We're used to seeing this in equations: input x, output y. So maybe our rule was like 2x plus 1. So if we input a 7, we're going to output a 2 times 7 plus 1 and get 15. To find the domain of a function looking at a graph, sweep from left to right and note locations where the function exists or is defined. So I've got several examples down here, and we'll talk about them. So as we sweep from left to right, what we have is the function has x values, x values, x values, x values, x values, and it just goes on forever in both directions. So our domain is all real numbers. On the second one, if we go from left to right, we have x values all the way up to 2, and we jump down here, but we haven't moved right any. So we keep going and have x values, so our domain is still all real numbers, even though we had to jump. Whereas in the next example, we have our x values all the way up until 2, and then we have to jump to 3 and continue on rightward. So our domain is going to be from negative infinity to 2 and 3 to positive infinity. And since they're filled circles, we include 2 and 3, a closed interval. In the third diagram, what we have is something that starts at negative infinity and goes all the way to positive infinity as we move from left to right, except there's a hole at 1, so we could say the domain is x does not equal 1. Another type of discontinuity would be a vertical asymptote, and the graph starts at negative infinity and works its way rightward all the way until it gets really close, infinitely close to the asymptote, and then it disappears and reappears on the other side of the asymptote and continues to exist all the way to the right. So this is another domain where x does not equal a value. And here's a function. This is a square root function that's been shifted right 5 units, and as you can see, there's nothing over on the left hand side, but there is stuff on the right hand side starting at 5 and going on forever. So we say the domain is x is greater than or equal to 5. Okay, for range we're going to do a similar thing, but we're sweeping from bottom to top. So what we want to do is start at the bottom of our function and work our way upward. And in this particular case, it goes from top to bottom indefinitely, so we can say our domain is all real numbers. In this square root function, we start at the top and we come all the way down to 0 and then go back up. So our range has to be y is greater than or equal to 0 because the lowest point is 0. All other values are higher than 0, all other y values. In the third example, we start way high, infinitely high, and come down all the way to 0 and then go all the way back up. But there's a hole here. And some would say, oh, we should exclude the hole, but if you notice, the hole has a value over on the other side that does exist. So while it may not exist on the right-hand side, it does exist on the left side, so our range is still y is greater than or equal to 0. If you had the instance where a hole existed on both sides, then you could call that out, but it does not in this one. All right, in the next one, we have a step function, which has lots of discontinuities. So you go this far, and then you jump up, and then you continue rightward, and you jump up, and you continue rightward, and then you jump up. So it looks like this step function exists only on the integers. So while all x values are covered, the only y values that exist are integers. So the range is the set of integers. Remember, the notation z means integers. And a reminder, integers are like -3, -2, -1, 0, 1, 2, 3, etc. Right. In the fifth example, we have something that starts at the top at infinity and comes all the way down. It has a hole at 5, comes down, sweeps up, and then keeps going downward again. So the only spot that it does not exist is at y equals 5, so we say our range y does not equal 5. In the final example, we have another root function, and in this root function, actually let's scroll up, it's more than just a root function. What we have is the function starts low and it continues to exist all the way up to -1, but does not include -1, and then it jumps up to 0 and continues to exist from 0 on upwards to infinity. So our range is from -infinity all the way up to -1, not including, in union with 0 all the way up to infinity, including. Okay, some tips. Recognize that your graph is reasonable. So if we have an intuitive understanding of parent functions and transformations, we should be able to start to recognize reasonable graphs. And then also you want to make sure that you see all the key features of the graph. If you know it's like a 4th degree polynomial, don't just look at this on your screen, because for all you know, the polynomial, since it's 4th root, could come all the way down here and continue back up, and it would be really sad if your viewing window only caught that much of the graph, because you would answer wrong. So interpret the meaning of those key features and then understand the limits of your grapher. That means sometimes your grapher may appear to be presenting the wrong answer, so you need to explore it better, particularly with TI graphers and their limited resolution.
Hey, Ron.
Hey, Billy. That hurt.
All right, when we want to find domain and range algebraically, it's going to require a little bit of analysis of the given function. Things I like to look for are dividing by 0 errors, or taking the roots of negative numbers, more specifically even roots of negative numbers. And also, particularly with range, the effects of even powers. So let's take a look at the examples. It says find the domain of the given functions. So in the first example, we have a root, a even root. So we do not want to take a even root of a negative number. So the inside, x plus 4, has to be greater than or equal to 0, and that gives us the domain of x is greater than or equal to -4. In the second example, I see a denominator, so we want to avoid having 0 in the denominator. So either x or x minus 3 cannot be 0. So we say x does not equal 0 and x does not equal 3. And the final one we have, this should say f of theta. F of theta is tangent theta. And since tangent function is y over x, you can think of this as a fraction with a denominator, and you want to avoid spots on the unit circle where the denominator is 0. So that would be at x values of 0 here and here, or if you thought of this as radians, pi over 2, and then 3 pi over 2. And if you want to be more specific and capture all of them, or I guess the right term would be more general, you're going to do pi over 2 plus pi times a number. So you get to this value, and then you add pi, add pi, add pi, add pi, etc. So sine and cosine don't have domain restrictions, but tangent, let's write these down. Tangent, cotangent, secant, and cosecant all have domain restrictions having to do with dividing by 0. So make sure we look at those domain restrictions. And finally, we want to be able to find the range of a function algebraically, and this requires a little bit more analysis, and so generally the problems I present will be pretty straightforward and obvious. For example, the square root function, anytime you take the even root of something, you're going to wind up with an answer that is, at the very least, greater than or equal to 0. So we can say that this domain is greater than or equal to 0. Jumping down to the bottom one, which is very similar, we can also still say that the range is greater than or equal to 0. So what we have is something that maybe does that. However, because what we have inside may create a negative answer, it is entirely feasible that the graph stops short of getting down to 0. So a little bit more further analysis is needed there. We're not going to go into it, but very loosely you can find out what the domain is of the function and then plug in key points of the domain to find out what the y values might be. So looking at the second example, we have a root function that we've shifted up 2 units. So if we take our square root and move it up 2 units, we find that our range is y is greater than or equal to 2. And the third one, we have an even power, and the even power of any real number is going to be positive. So we finally arrive at y is greater than or equal to 0. One last quick example. We'll just say f of x is equal to x to the third plus 2x squared minus 8. We should remember that the domain and range for all polynomials is all real numbers. All right, this concludes the lesson for Skill 105. I can find the domain and range of a function graphically and algebraically. And as I mentioned before, we have the Greek temple, the Parthenon, and the stylobate is being bowed here. And when they built this temple, they actually curved the base and the top of the temple so as to create a subtle illusion, because without that bowing, the temple looks like it actually sags under the weight. So visually it looks to sag or curve downwards. So by creating the counter bow, it helps keep the temple look like it is an even straight line across.